Good evening. Welcome to the January meeting for Silicon Valley Asymptograph. Tonight, we will have an exciting presentation by Suyeon Choi from Stanford, who will tell us about his latest research in VR. For those of you who have been attending our meetings regularly, you may remember that Suyeon previously talked about using AI in VR. If you're interested in Suyeon's previous presentation, you can find it on YouTube. Just search for Silicon Valley Asymptograph on YouTube, and our channel should appear near the top of the search. I am Alex Junkarek, Chair of Silicon Valley Asymptograph. Before we get to tonight's presentation, let me tell you about our chapter. Silicon Valley Asymptograph has been meeting at different Silicon Valley companies such as NVIDIA, Apple, Intel, and Google for many years. However, since COVID hit, we moved to online meetings. This year, we would like to return to in-person meetings and are looking for locations where we can meet. Typically, this requires for an employee of the host company to sponsor the meeting. If having Silicon Valley Asymptograph at your company sounds interesting to you, and you would be willing to help us out by sponsoring us, please contact us. Our contact information will be in the next slides. Now let me introduce the officers of our chapter. I am Alex Junkarek, and I'm the chair of the chapter. Brent Simon is vice chair. Carl Anderson is treasurer. Sharon Yang is secretary. Ken Tchaikovsky is a member at large. And finally, this could be you. We are always looking for more volunteers and need help in many of the chapter activities. Particularly, one way we could use help is in finding venues for in-person meetings. If you like what you see here, or even if you would like to see something different, please consider joining us. You can find the latest information on our chapter on our website. We also have a meetup where meeting information is recorded. You can contact us using this email. We also have a YouTube channel where many of our events are recorded. If you're watching this on YouTube, these links will be in the comments and in the YouTube channel description. Otherwise, you can find this information later by entering Silicon Valley Asymptograph into Google. Now I'd like to tell you about some of our future events. SIGGRAPH Asia occurred last month in Hong Kong. In February, we're going to have a recap of this event given by Thomas Bednars, who talked about revolutionizing scientific discovery with simulation and AI in last month's meeting. Stay tuned to our meetup for more details, and please join us in February. And now I would like to introduce tonight's speaker. Tonight, we will hear from Suyeon Choi talk about Gaussian Splats for ultra-thin holographic glasses. Suyeon is currently a postdoctoral scholar at Stanford Computational Imaging Lab, working with Professor Gordon Wettstein. He is broadly interested in developing new algorithms and optical systems at the intersection of graphics, optics, AI, and vision science. During his PhD, he developed holographic display systems based on AI for VR applications, for which he received the ACM SIGGRAPH Outstanding Dissertation Award Honorable Mention in 2025. He earned his PhD from Stanford University and undergraduate degree from Seoul National University. He will be joining the Department of Computer Science and Engineering at Seoul National University as an assistant professor in March of 2026. And so now, please welcome Suyeon Choi.
Thanks, Alex, for the introduction. Let me share my screen. Hi, Suyeon again. Hi, everyone. I'm Suyeon again. So I think I gave another version of talk in this seminar series like a year ago. And since then, I have had a few updates along the same line of work, which I'm very excited to share with you today. So displays are this primary interface between the computers and humans. So as AI agents become more capable and increasingly integrated into our daily lives, they will communicate with us through ever richer and denser visual information. So in the near future, it's not hard to imagine that we'll see a new interaction paradigm enabled by these glasses-like devices. allowing us to engage seamlessly with the AI agents through augmented or mixed reality or WarMars. So for these systems to be successful, they must fit into a comfortable everyday glasses form factor. So something we can wear for hours at a time. So that means that they need to be thin, lightweight, and ideally support visually comfortable features such as vision correction. And also these displays must go high quality. So they need to faithfully reproduce all the full set of visual cues that our eyes rely on to see the world. So depth and focus cues, ocular parallax, vivid color, wide dynamic range, and occlusion. So essentially everything we see from our real world. So however, that's not what we see in the market. So and achieving these perceptually realistic images within such a compact form factor is still an open challenge. So there's no clear path towards realizing this vision. So today, I'll be directly talking about that this holographic glasses prototype can show some promising progress towards this goal. So what we showed earlier was that it can achieve extremely thin form factor with an optical step of only 3 millimeters, while enabling visual cues that conventional displays cannot reproduce, such as this large parallax or proper focus cues as you change your focus states. So this is enabled by a fundamentally different principle from what is used in most current mirror displays. So this is called holographic principle. So here I'm showing a short clip from YouTube video of a static hologram created using this principle. And this principle was invented like a century ago. So what we saw was that here behind this glass, there appears to be a three-dimensional object. So as you move your head, you can see how the light interact with the object, and then that's reconstructed by only a thin film. So you see this parallax and white light interaction effects. But what's noticeable was that in reality, what's behind the glass is just a single laser and a thin recording film. So inside this glass, there's only a single piece of film that has been created or exposed in a very special way. And this can encode the entire three-dimensional scene. So let me talk about it a little bit more. So this is called the like holographic principle. So and I will show the way we record the hologram. So we will use two beams that are projected onto this analog holographic film that we just saw. So one is this reference wave. This is just like a plain wave of the laser. And the other is this object wave scattered from the object itself. And then this film can record this interference pattern of these two beams. And this is what we call analog hologram. And then if we once we record it, and then we can just replay this 3D object by just shooting the reference wave again. So this is the basic principle of holograms. And but these are like static photos. So this is like analog static hologram that we cannot really play video error. So it's not really interesting. So people have been interested in moving this from photographic holograms to digital displays. And then the main idea is to replace this film with the dynamic displays. And that's usually a spatial light modulator or SLM. So this SLM usually controls the phase of the light, or it can also control the amplitude of the light, like normal TV. And then instead of like recording these interference patterns optically, like what we just did, we can now compute the phase pattern digitally, maybe using some computer or algorithms. And then with this phase pattern calculated and displayed on SLM, like just like analog film, to reconstruct this 3D scene, we can again shoot the laser onto the SLM, and then this modulated phase can create 3D holographic images, but now dynamically. So we started with these glasses. So and then applying this principle to glasses is also described here. So here we use the laser, and there's a collimation optics that do flat the wavefront, and then SLM controls the wavefront of this laser beam, and then this wavefront continues to propagate and then create these 3D holographic images in the air. And that's usually seen by the user through an eyepiece in near display settings. So this is the basic principle that we are gonna see throughout these slides. And as I mentioned earlier, this principle was invented nearly a century ago. So it was invented in 1940s, but it has not become mainstream until now, partially because like until only a few years ago, it was not really possible to generate these high quality images for dynamic holographic displays. So this was the good example published in 2019. And also, there are many other challenges that still need to be addressed. So first, these systems are typically demonstrated on a very large benchtop setup, so which is very far from a glasses-like form factor. And then second, this image quality was low, but also there was this limited attentive. So which means that this number of pixels in the display determines this amount of information, and then that determines the combination of field of view and then the eye box where we can see the images. And then they are typically pretty far from what we expect from the good AR and VR displays. And also, they struggle to handle complex and real world scenes. So they are not scalable to what we see from the real world. So these are big challenges. So today I wanted to show how these technologies has been developed for the last years. So first, I will present this several like promising AR and VR prototypes based on this holographic principle that achieves very ultra thin form factor. And then I will show how we can really, using algorithms, how we can really encode and decode these high quality visual cues, such as this parallax and then focus cues. And then finally, I will introduce an algorithm that converts the latest neural rendering 3D representation into holograms that we are interested in. So first, I will talk about like our optical design first, and then typically like the AR and VR displays rely on this magnifier principle. So the basic idea is that the images must lie directly on the display panel, and then this display panel requires a gap between the focal eyepiece about a focal length. And then we also saw these pancake lenses to shorten the focal length a little bit, but there's still a gap and a significant gap. And then these systems often remain very bulky and heavy. So, and on the right, I'm showing the holographic pancake lenses proposed a couple years ago, a few years ago. And this is interesting for achieving lightweight form factor, but they still rely on 2D displays and then cannot really reproduce the true visual cues. So our latest paper combines waveguides and then this holographic optics and also digital holography using SL lamps to create true 3D images. But also this design allows us to eliminate the gap between the display and eyepiece, enabling the ultra-thin optical stack. So here's more detailed view of our latest design. So it integrates a laser, MEM scanner, and waveguides, an SLM, and holographic eyepiece lens, which is exploded in here, in an ultra-thin optical stack. And we prototyped this design with the Changwon Zhang and Douglas Laman at Meta Reality Labs. And then I'm going to show the results captured in this prototype. So here is how it works. So we again, so the main principle is the same with what I showed earlier with the basic illustration. So we have a laser and the waveguide, and the waveguide has two couplers. So typically it has in coupler that guides this parallel beam into the waveguide, and then the beam continues to propagate. And then whenever it hits our coupler, it is designed to direct the beam into one direction. So here the beam is continue to propagate, and whenever it hits the outcoupler, it outcouples towards the direction of the SLM. And then the SLM controls the phase of the light and then creates the 3D holographic images in the air. So the waveguide should be designed to output the light in only in one direction towards the SLM. But usually, like these typical diffraction gratings couple multiple diffraction modes into and out of the waveguide. So this leads to this bidirectional light leakage, and some light escapes towards the outside world, and some leaks towards the viewer's eye, which is this direction. Um, and this is like typically what we see as a glow in AR waveguide glasses. And this works as the same principle, and we don't want this. So we address this by designing this angle encoded like holographic waveguide with a volume grading coupler. So this is totally different from the conventional gratings, and is actually recorded an analog hologram that I showed earlier. So the main benefit of this is high angular selectivity, and this break grading is designed to outcouple the light into only a single direction, which is upward, shown here. And then these eyepiece, conventional diffractive lenses can achieve very thin form factor, but they suffer from this severe chromatic dispersion, degrading the perceived image quality. So if you have like a certain period of this diffraction grading, the wavelengths actually creates the focal spot at different distances. And then we also employ this holographic principle to create this apochromatic imaging characteristics. So our lens is designed to provide the same optical power for three narrow band laser sources that match the wavelengths of our holographic waveguide design. So here's our final design, but there's one missing feature that needs to be really carefully addressed, which is called attendue. So this is very important design parameter for all the optical systems, and it describes the information capacity of display and can be calculated simply as a product of this field of view and eye box. And for a given display, unfortunately, this attendue is the constant because it boils down to be the number of pixels in the display. So one can use the different eyepiece to trade off between the field of view and eye box, but this total information cannot be expanded simply. So there are many proposals for increasing this attendues, but here what we advocate is that to achieve this high image quality with the large attendue with the thin form factor, we propose to use beam steering with the MEMS and combine with the high-speed SL lamps to create this large baseline light field with the high image quality. So by synchronizing this SLM and the MEMS scanner, which is shown here, we can effectively create the synthetic apertures that are mutually incoherent. So this enables partially coherent holographic display modes that maintain high image quality across the large attendue. So with that prototype, here we demonstrate that it can support the large eye box, which is much larger than conventional displays, which is shown on the left. And then what that means is that you can see images more comfortably in a more accessible eye box region. So here is the prototype that we made. And also like we explored like the similar concept, but for this AR display setting. So this combination of waveguides and holography for AR applications can enable this high quality 3D images in a very thin AR glasses form factor. And this was published in Nature a couple of years ago. So to summarize, this combination of waveguides and holographic principle is extremely exciting. And then I believe this opens up many untrivial opportunities, including these ultra thin form factors that I showed earlier. So that wraps up the first part of the talk. And the takeaway is, again, the waveguides plus holography can uniquely achieve very advanced optical design like thin form factor. And then next, I'm gonna talk about like how we can actually achieve this like unprecedented like visual cues like parallax as you move your eyes. The images in real world changes, so the images from your display also should change based on the depth, and also the focus cues as you change your eye states, focal states. The images arriving at your retina also changes. So that's naturally supported by the real world, but not by the conventional displays. And I'm going to talk about how we can support it in holographic displays. So, interestingly, in holographic displays, this is primarily an algorithmic challenge. So, this is solving the algorithm problem. So, we want to develop an algorithm that converts this 3D scene input because, like, the input for this holographic display system would be the 3D input, but for the output of the algorithm would be the holograms or the phase patterns that we want to display on the SLM. So, what algorithm does is that calculate the right phase patterns for SLMs. And then this should be encoding this all the visual cues and then from the 3D scene or the real world scene. And then intuitively, what this does is that just like optically backpropagating to the film in analog holograms, we would numerically simulate the wave propagation from the scene to the SLM. But these traditional CGH approaches often rely on some heuristics for these phase distributions or the encoding tactics for the SLM, which limits the overall image quality. But with the this gradient descent framework, which is widely used in machine learning, what we can do is that uh, predicting this light distribution across the 3D boxers in a more principled way, and then we can calculate the loss between the target, which would be also rendered from the our 3D content using the rendering, and then we can indirectly optimize for this 3D content using this loss function and gradient descent backpropagation. And then this usually works pretty well. And then what we showed earlier, like a few years ago, was that if we optimize these SLM page patterns for the 3D boxers uh, with some fast SLMs, um, we can achieve this very high image quality holograms that supports the focus cues. But the thing is that though this is captured with the fixed viewpoint in a very limited setting. So what we need for a large attenuation setting, as we said earlier, because our prototype can support this large eye-box attenuation, and one missing feature was this parallax. So in a large attenuation setting, if your users can move and rotate their eyes over a wide range, uh, they will see this parallax. So closer objects would move like more widely than the further ones. So we need a little bit advanced algorithm than normally optimizing for 3D boxers because that doesn't tell these angular light distributions. So, but the more complete representation of the spatial angular light distribution is the light field. So here, what we could do is that we can, instead of predicting the 3D boxers, we can predict blurred light field from these holograms, and which I will tell you about later. And then still compare this end-to-end full light field target with the predicted simulated light field using the same loss function and backpropagate towards the holograms that we want to display on the SLM. So this is the same algorithm, but this the target is rendered to have more complete angular information. So, and then at the core of this is that how we can actually predict this light field, because light field is intensity over the different angles. But this holograms works in a wave optics principle. So we need to bridge this wave optics with the light field. And that's done by Zhang and Leboy at like a decade ago. So we know that this fully coherent wavefront itself doesn't have any this angular effect or direct effect. But the intuition here is that if we have like finite aperture over this full aperture, you can effectively introduce this dimensionality into the system. So here, what I'm saying is that if we assume this finite pupil, the views observed from these different view positions can be interpreted as a samples of these different angular components of the wavefront. So what that means is that we can low pass filter in the wave domain and then extract these light field views from these angular samples. And that's called the like observable light field. And then we can stack all the views by passing through these partially coherent wavefronts in the Fourier filters with the angular viewpoints. And then that's how we would compare with the light field with the target light field rendering. But the problem here is that there is like this crosstalk between the apertures, and then they would effectively lower the contrast, but also it has never compared with the full resolution target. So if we do this naive light field supervision, typically it shows the lower resolution. So what we proposed is that instead of simulating it through individual apertures, uh, we look at the simulated light field view with the synthetic aperture. So that's why we named the uh, paper as a synthetic aperture holography with the waveguides. And then what we are going to do is that we compare these simulated light field views with the synthetic apertures with the rendered views also through the synthetic apertures. And then if we do that, this synthetic aperture holographic algorithm shows the accurate view-dependent effects. So for example, if you do 3D voxel optimization for holograms, it can do something, but it shows some hazy result if you see on the trunk, and also this parallax is not correct. Compared to the naive light field algorithms, ours can show higher resolution and higher contrast. So this is another result showing the robustness of our algorithms. And actually, like all the results that I showed earlier was captured experimentally, and that was fairly good. But achieving this high quality experimental result has been very challenging for last few years, as I also showed in the very beginning. So this is often because of the model mismatch between what's happening in the experimental setup and the model that we use to simulate the optical propagation. And then what we came up with the last year to solve these long-standing challenges is to use this hardware feedback um, to train this model to match our optical setup. So what we can do is that we parameterize this optical simulation model pipeline and then train this model to match the data captured from our setup. So here's a little bit more detailed parameterization that I said earlier. So what we are going to do is that parameterize the wavefront in Fourier domain or angular domain or this primary spatial domain at the SLM. So this would represent the laser beam wavefront, and this would represent the Fourier wavefront. And then there were some CNNs to account for like other mismatches that are hard to explain. And then what's interesting is that if you train these parameters using the data from captured from our setup, it can really learn useful prescriptions from the physical setup. So for example, we never show this iris in the setup directly to this model. And this was just put in the setup, but never shown to the model directly. But so model only saw the pairs of phase patterns and then capture the intensities. But it can really recognize the blade shape of this iris at the Fourier plane. And this was demonstrated on a very typical benchtop prototype, but actually applying these models to more complex setup, something like this, is not trivial because the wave propagation here is much complex, and also the training takes a day, and it's not really scalable to large attention setting. So we have to do something here. So one thing we realized is that most of this model mismatch comes from this partial coherence. So this setup actually exhibits a much partial coherence than other setup because there would be some optical path length difference between these outcoupled beams. And so the output of these waveguides has like features of this interference of multiple beams out of the wave propagation, complex wave propagation inside the waveguide. And then this partial coherence would be represented completely with the term called mutual intensity. So what this mutual intensity tells us is that the how much two beams at two different locations would interfere each other. So if they are coherent, they would interfere each other, and then if they are incoherent, they would end up being zero. But the thing is that we have a MEMS scanner to steer the light, and then the output of this waveguide also depends on the angular intensity. So this would be computationally very prohibitive to store. And then what we proposed is that actually this mutual intensity can be vectorized in a very low rank manner. So, and then that can be represented with the only handful of wavefronts, like what we used before. So we are going to only learn multiple modes of this mutual intensity, and then that can save our computation much efficiently. So here, what we are going to do is that we reparameterize these wavefronts with the only handful of modes. And then what we realized is that we can actually leave out the CNN components. And then this model can generalize uh, better and then can be trained with the much less number of the training data. So here I'm showing the learned intensity. So this is the visualization of our model output. So, but you can see that it can represent the physical properties much better, quite faithfully. And then using this model, we can achieve fairly high image quality, which was not possible using the conventional analytical model before. So that wraps up the second part. So what we showed was that we can achieve high image quality over a large attendue using advanced algorithms. And then next, I will talk about how we can turn this representation from the latest neural rendering techniques into holograms. So the motivation of this is that, so we saw that computer-generated holography can encode good parallax and focus cues if the data representation has those information, visual information. But actually, it can turn any like computer graphics primitives into holograms. So for example, you can turn point clouds and meshes into holograms, and then people have derived the how you can turn these renderings or 3D data itself to wavefront representation. But the problem of this is inherent to the input itself, because some of these like data types do not natively support view-dependent effects. For example, point clouds cannot really support occlusions because you will face many holes over there and occlusions. And some of them are not scalable to photorealistic scenes because they are not really easily optimizable for real-world captures. Light fields theoretically can do that, but this is really extremely slow, and then the memory I/O constraint is prohibitive, and the dense light fields are not readily available. And recently, advances in neural rendering have made great strides in improving the quality and efficiency of this 3D reconstruction. So Gaussian splatting has emerged as a state-of-the-art neural rendering method that turns a few photographs of the scene as an input, and then use these differentiable volume rendering techniques to distill these multi-view images into a 3D representation, which is the collection of Gaussians. And then it achieves also very fast rendering time by leveraging this explicit primitive-based representation and suitable for a variety of computer vision and graphics tasks. So this has been established as a representation of choice for many applications, for many great features like computational efficiency, high image quality, interpretability, and robust tokenization behavior. So here we developed a technique, CGH techniques, computer-generated holography techniques called Gaussian wave splatting, and that turns these Gaussians into holograms. So the contribution of this work is the development of this efficient Gaussian to hologram transform, and then this method can inherit all the benefits of ray-based Gaussian scene representation for wave-based holographic displays. So here is our teaser result, and this enables us to render photorealistic 3D holograms. So in other words, all the Gaussian splats that you saw earlier was all 2D projected on your TV screen. But now you can see these Gaussians truly in 3D. So this is exciting. So why this is efficient is that, so if you think about this live field CGH, you would have rendered this full target from this 3D content that would have been already inefficient. And then you compare the simulation live field with the target and then backpropagate them. So this would take a while, like it might take even an hour. But in our technique, we directly take Gaussian parameters like positions and rotations and scaling of Gaussians as an input and directly create holograms. So this could be much efficient. So to do that, what we had to do was to derive the transformation from these Gaussians with the arbitrary rotation and scaling and translation, and calculating this wavefront footprint at the SLM. So this is a little bit of math, but I'm gonna go through it real quick. So to derive this closed form solution, where we start is that this canonical Gaussian, because this canonical Gaussian has a closed form solution in a very neat way, because the Fourier transform of Gaussian is also Gaussian form. So we start with the very unique Gaussian without any scaling and translation. And then if you scale this Gaussian and make it anisotropic, these wavefronts or angular spectrum of the scaled Gaussian can be computed by sampling at an inverse transpose coordinate in the angular coordinate. And then there's also another Jacobian scalar term because of the coordinate transform. And then we are going to account for this rotation of the Gaussian to calculate the wavefronts. So key intuition here is to look at the single frequency component, which corresponds to the single plane wave. And then this perspective aligns with the angular spectrum, because angular spectrum is really the just collection of the plane waves. And then this k vector follows the relative rotation between the two coordinates. And then angular spectrum in the tilted plane, which is denoted as a like y here, can be obtained through the nonlinear mapping of the angular spectrum in original coordinates, which is shown here. So here again, there's another Jacobian term from the coordinate transform. And then lastly, we are going to account for the translation. So far, we accounted for rotation and scaling. And this is pretty straightforward because we can just use the well-known angular spectrum method. And in angular spectrum domain, this just applies for our phase ramp. So, and then this is the final closed form solution that we derived to enable this transform from Gaussian into the wavefronts. And then what we are going to do is that add up all the contributions from the Gaussians, from the Gaussian input. But that unfortunately doesn't work because this doesn't account for the alpha compositing or alpha blending that's used to calculate the original Gaussian splats. So in standard alpha blending, so from the rays shoot from each pixel, camera pixel, they are cast through the scene, and primitives intersecting the rays are accumulated through the alpha compositing, which you may be familiar with. And then we derive the wave-based counterpart of this classic volume rendering equation, which is the alpha blending equation. So here we instead propagate wavefront and then hit each Gaussians and accumulate the contribution of the wavefront analogously following the alpha blending principle. And then this allows us to accurately reconstruct the 3D scene, matching the original target rendering. So, but one like downside of this is that this wave propagation through all these primitives can be computationally prohibitive. And then what we did is that we were inspired by this older invariant transparency technique, which was also used to speed up the rendering. And then this can speed up the this rendering like much faster, like 30 times faster. So while keeping the image quality pretty the same here. So we compared our method against prior primitive-based EDH methods using the same number of primitives and observed the significant performance improvements. So with the point cloud method, the size of this each point has to be tuned for this visibility test. And then these polygon-based methods require like per triangle texturing, and then resolution of these texture matches are often not enough to match this photorealism, while our Gaussian wave splatting can reconstruct these highly detailed appearances. So here we show that Gaussian wave splatting or GWS can achieve accurate 3D refocusing effects from arbitrary lower viewpoints, demonstrating the robustness of our method. And here's another scene that I showed earlier. So this wraps up my talk. So there were a few messages, takeaway messages, I think. And the first was this: the combination of these waveguides and holography can uniquely enable ultra dim display form factors for AR and VR. And then these advanced AI algorithms plus optics together provide this unprecedented level of holographic light control and accuracy in free space, which enables the perceptually realistic images and also unlock many new exciting applications maybe. And then we developed this Gaussian wave splitting, which is much more efficient pipeline to generate these holograms. So this corresponds to each part of the display system. So what this display system does is that taking the 3D input, either from real scene or 3D content, and then output and create these 3D images optically through your retina. So, and then I framed it as a like some encoding part which encodes the 3D data into holograms, and then decoding parts which optically decode these holograms for your eye and visually. And then there were some these algorithms for modeling and learning, and then reducing the gap between the two. So that's it. And this was done with a lot of like amazing colleagues. And thanks for listening. And now I'm really happy to take any of the questions. Thank you.
I have a question. So does your display is it a VR display, or can you also use it for like AR glasses?
Oh yeah, so most of the result I show today is for VR, but definitely you can do AR. So I showed the AR glasses design here, but I didn't go into the detail, but I can maybe show some results out of it. So give me a second. So here I showed the AR glasses design, and then I will talk a little bit more about this. So AR glasses, what we proposed is that to push these beige SLMs right in front of the waveguides, and then the wavefront modulated here would continue to propagate this through the waveguide and overlaid with the physical environment. And then what this enables is that I'm not sure if I have good images here, but definitely check out the paper here, which was published a couple of years ago. And then, yeah.
I have a question about the rendering.
Mhm.
I know there was a time when holographs were a single spectral sample, and then there were white light holograms. Are there any issues with rendering for over across the whole spectrum. Like I thought I saw some kind of artifacts that kind of almost look like over sharpening artifacts that were in the Gaussian splatting rendering. I don't know whether it was zooming in and out or doing something like that.
Oh,
Some
right, right,
kind of
right. That's right.
lattice
Yeah,
overlay or something. Can you comment
exactly,
on that?
exactly. So that's a great question. So,
Yeah, yeah,
uh,
this is it.
here, like if you see the boundaries, like these edges are not like exhibited as a natural thing, right? So, and I think this is much because of the some wavefront behavior that we actually assumed like uh, in our algorithm. So we assume some flat phase profile here, but
Okay.
this is not the case for other algorithms. So,
Mm,
and also this has been an open challenges, and I think many people are working on this to resolve this problem. But I think this is definitely a solvable problem. And also speaking of this, like white light sources, what
right.
that can provide is the some types of partial coherence. So it would provide the broader range of the wavelengths, and then that can actually effectively works as some blur. So you might reduce it might reduce some resolution effectively, but also can um, hide this like spectral artifact because it's multiplexed over a wide range of the wavelengths, I think. Yeah. But I think a baseline like it provides another degrees of this coherence, which could be useful or might not be useful also.
So if I understood you correctly, in the background here where the plants are or the lawn, that texture that's there is due to your assumption that that's planar and whereas it's not planar. Well, oh yeah, why is it getting sharper
Oh, yeah.
occasionally?
So here, actually, what we are doing right now is that we are changing the focus of the camera. So I
Okay,
think here, I think the camera is focused on the front here.
right,
And
okay,
then as we change the camera, focus to the background. I
okay.
think this bore, I think got sharp, but while we got blur in
Mm,
the foreground, right? So, but unfortunately, the blur behavior is not really natural
okay.
because of
Right, it's
this
not
phase
Gaussian.
assumption. Exactly, exactly. So, people would assume some random phase profile to make it more Gaussian-like features, but here we assumed some artificial like phase profile here.
I
Yeah.
got it. Okay,
Mhm.
yeah,
Thank you.
that makes sense. Can you say anything about the frame rate of rendering? Can you do real-time rendering or
Oh yeah, so there has been many exciting work using this like deep neural networks or CNNs that enable this hologram rendering in real time. So definitely it's possible rendering, but also the image quality of those renderings are a little bit limited. So the rendering time I showed earlier, or most of our work, is like takes a second or minute, and this Gaussian rendering also takes like right now a second or 2 minutes, and that's a very exciting problem to solve. Yeah.
okay? And I guess for rendering, you are well. You mentioned light fields and the phase patterns and the Gaussian splatting. Are they
Mhm.
all incorporated in your rendering, or
Uh, so I think the principle is basically the same. So you predict the wave optics prediction and then try to match that with the either light field or Gaussians, right? Uh, but uh, this each algorithm uses takes like each 3D representation. So some CGH algorithm can take these light fields as an input and create hologram,
Mhm.
but this Gaussian wave splitting algorithm takes Gaussians as an input and outputs the hologram. So you can see this as a two separate CGH algorithm, but outputting the same holograms. Uh,
Right, right,
if you have like different rendering output, of this light field and or native 3D Gaussian representation. Yeah.
Got it. They both have the hologram output.
Exactly. So two different CGH algorithms, but output the same hologram. Yeah.
Okay.
And then there might be some trade-off between the visual quality and the runtime.
Good.
So I have a question. Will the Gaussian wave splatting, like effectively, like can you see like reflections and refractions using that technique?
Oh yeah, absolutely. But so Gaussian splatting supports these like specular reflections and angular effects, and then that's incorporated in the spherical harmonics coefficients. And then our Gaussian splatting can also support that. But the problem is that this attenuate or limited, like the range of your eye can move is very limited. So the specular highlights are not really best exhibited here, but theoretically it's possible. Yeah, that's a great question, I think.
Hi, Sion. That was an amazing talk. I do have a question about the inputs. Do the inputs have to be static when capturing?
Uh, input. Uh, so like this can be like a dynamic display. So if you change these phase patterns, the
Mhm.
output images or this holographic image changes. So what that means is that you can just cycle through the uh, SLM patterns and then can actually display this 3D video. So here, the phase patterns displayed on the SLM is the same, but we only change the focal states. But here, from here, okay, so here, from here to here, we are showing the different display patterns, and then of course you will see the different images here, different 3D boxers.
Ah, I see. Okay.
Yeah, and then of course, like the input of this would be different from the input of this, right? So and then they are different 3D scene representation, and then that would correspond to the different holograms. Yeah.
Great.
Um,
And can I ask my question about the garden scene there with the ringing around the plants? I guess you already answered that in
Yeah,
terms
sure,
of
sure.
so is ringing a proper term for what the artifact is there around the
Sorry. I think it's called like ringing artifacts in holograms. I think that's the term people widely used for these artifacts. Yeah, ringing artifacts.
very impressive talk. amazing work in all those fields there. Thank you.
Thank you so much for having me. Yeah, again. Yeah. Hopefully I can come back with more exciting work in the near future.
Yeah, definitely.
Sounds great. How heavy are the holographic glasses? The holographic headsets that you built. You said it's very lightweight. It looks very small. Do you know?
That's a 3 millimeter thick, right? I was seeing in the diagram, the exploded view, right?
Yeah, right. So this optical stack. So this looks like this here. Yeah.
And that's comfortable for all day.
Yeah, but one thing like they really need to carefully address is that it uses laser. So you know, so I think this safety issue also needs to be carefully addressed, I think.
Okay.
But also like these components are also pretty expensive, I guess, to be mainstream yet. And also most significant issue right now is the attenuate that I said. So and the robustness of this calibration and rendering and so on and so forth. Yeah.
Is the antenna used for sending the image or positioning or
Yeah, so
what's
this is for this streaming this phase pattern for the SLM, this part. And then this wire is for laser.
Okay,
You
thank
can
you.
also like put like prescription lenses in there also. If someone
Oh,
needs
yeah.
regular
So,
Yeah, I was gonna
okay,
follow up.
that's a great question, actually. So, one great feature of a hologram is that actually you don't need a prescription lenses. So you can actually prescribe your vision into the software, and then the images can be corrected, like dynamic, based on your vision. So that's one good thing. And then, yeah.
You know what you plan on doing in your new position, future there, or are you open to
Oh, yeah.
explore?
So, yeah, I think I could mention this. And then I'm joining the Seoul National University, where is my alma mater. So, in a month, actually. So, I'm very excited to continue this holographic thrust in my new lab, and then continue to research on this. But also very interested in like branching out based on this paradigm of combining optics and AI or physics and AI.
That sounds really exciting. Good luck next month.
Yeah, thank you so much.
Yeah.
Awesome. Then I will start my screen sharing.
Does anyone have any more questions?
Will you be coming to SIGGRAPH?
Oh yeah, I think I'm planning to go SIGGRAPH. I also went to the SIGGRAPH Asia in Hong Kong. That was like fantastic. And then
Oh yeah.
yeah, hopefully I can catch up there. Yeah.
Awesome.
Awesome.
Maybe you can join our next meeting and mention things you saw there.
Yeah, I mean, I didn't really go to the technical session though, but Hong Kong is such a nice city to visit. So
I believe next year, or actually rather this year, it's going to be in Malaysia, Kuala Lumpur.
oh right. Yeah. I'm also very excited to get there. Yeah.
Well, thank you for speaking with us, Suyeon.
Yeah, yes. Thank you for coming again. It was really exciting to see you again, and good luck in your new position. I wish we could have you again, but I mean, if you're welcome to come anytime if you want. The time difference might be huge between here and Korea, but yeah, you're welcome to join us, and we would like to. We would like see you more of your work at SIGGRAPH, hopefully.
Absolutely. Thank you so much again having me and then hosting this great event. Thank you so much, everyone.
Thank you.
Okay. Thank you all for coming, and yeah,
Bye.
okay.
Bye bye.
Okay, good night.